Chapter 5, Covalent Bonds and Molecular Structure. So in the last chapter, we learned how to draw Lewis structures. And so now we're going to take it a little bit further and discuss some different bonding theories and how we can predict shapes. So the first theory is valence shell electron pair repulsion, or VSEPR. So we can predict the geometry, we can predict the shape of a molecule by looking at bonding pairs of electrons and lone pairs of electrons. And we call these domains. So for example, we have two double bonds here. We have two charge clouds, or two domains, on the central atom, right? So we have this oxygen atom, this oxygen atom. Here we have a double bond and a single bond, and one lone pair. So how does this affect the shape? We have a total of 3 charge clouds, or 3 total pairs of electrons around the central atom. Remember, when we see double bonds, we treat them as if they're a single bond because they're located in the same space. We can look at ammonia here. So I have, once again, 3 bonded things and 1 non-bonded thing. 3 single bonds, 1 lone pair, 4 total charge clouds on the central atom. So how do these different things affect the overall shape of the molecule? So on the sheets that I gave you, on those shape sheets, I said we're not going to really worry about the charge cloud geometry. That's just looking at, for example, if you have 2 pairs of electrons, whether they are bonded or non-bonded, we would say it's linear. If we have 3 pairs, it's trigonal planar. If we have 4, it's tetrahedral. So those types of things just tell us the arrangement of all of the electrons, whether they're bonded or non-bonded, bonded or lone pairs. But what we care about is the actual shape, or the molecular geometry, which just really takes into account the atoms that are present. Now, we still have to consider those lone pairs of electrons because they actually take up more space, and we'll see they can push bonded pairs of electrons, those atoms, they can actually push them closer together. And we see this in bond angles, which measures the distance between 2 bonds, basically, on a central atom. So here, central atom, the distance between this bond and this bond is 180 degrees because it's linear. When we have a trigonal planar, we have the distance between this atom and this atom is 120. This one and this one is 120, and this one and this one is 120 degrees, right? So we make up a circle here. In a tetrahedral molecule, we actually see that the distance between our atoms in terms of bond angles is all 109.5 degrees. In a trigonal bipyramidal situation, we have what we call our equatorial atoms, right, which would be coming around the equator if we imagine this. They're all 120 degrees separating each other. And then your axial bonds, or atoms, are 90 degrees from each of the equatorial atoms. And the distance, or the bond angle, between this top one and this bottom one would be 180 degrees. So when we have an octahedral shape, we notice that the distance between all of our atoms in terms of their bond angles will be 90 degrees all the way around. So these are both charge cloud geometry, because if these weren't particularly atoms, we're still looking at the overall, where are the electron pairs. Now, when they are all atoms, then that allows us to design our geometry, or our shape. So we've had some practice with this. We draw our Lewis structure. We count the number of lone pairs of electrons, bonding pairs of electrons. We get a total pairs of electrons. And then we apply this VSEPR model, valence shell electron pair repulsion. We can determine the molecular geometry by considering the positions of the atoms only. So here we have a linear molecule, beryllium chloride. Here we have boron trifluoride, which is trigonal planar. And these are the instances on that first part of the shape sheet where we only have atoms present. So methane is tetrahedral, which is CH4. Phosphorus pentachloride, trigonal bipyramidal. And sulfur hexafluoride gives us an octahedral shape. So once again, those are all when we just have atoms surrounding the central atom. Those are our shapes. 0 lone pairs on the central atom. So what happens when we don't have just atoms? When we deviate from that? So here we have methane, all atoms surrounding the central atom. Here we have ammonia, where we have 1 lone pair of electrons, 3 atoms. And here we have water, 2 lone pairs, 2 atoms. So we notice that the more lone pairs of electrons we get, we see that the bond angle is going to decrease because these electrons are going to spread out. They have the option now. They're not localized in a bond, so they don't have to be that close together. Electrons repel each other, so they're going to take up more space when they can. So we see this pushing together then of the remaining bonded atoms, 109.5 degrees to 107.3 to 104.5. And we notice the shape is different too. Here it's tetrahedral, trigonal pyramidal, and bent. So we see the repulsion, which is valence shell electron pair repulsion. How are these electrons pushing each other out of the way to be the most stable structure they can? What type of shape are they going to take to minimize the electron repulsions? So bonding electrons take up less space than non-bonding electrons, or lone pairs. So this is the second side of the shape sheet. It's a lot of S's there. And we've looked at this. So this side here is the geometries or the shapes for when we have lone pairs of electrons. So we see we have a bent structure here, which is a 3-2-1, 3 total pairs, 2 bonding, 1 lone pair. We looked at these in the last 2 slides, the difference between trigonal pyramidal and bent. Once we get into having 5 total pairs of electrons around the central atom, we can have 1 lone pair, 2 lone pairs, or 3 lone pairs, and we see how that affects the shape. Notice these are pushed closer together because this pair of electrons is going to take up space. Here we have these electrons that are going to push all 3 of these bonds closer together. And here we see a linear structure based on the fact that these 3 lone pairs of electrons are going to kind of float out as if it's a skirt. And then our last one is when we can have a total of 6 pairs of electrons around the central atom. And when we have 1, we notice we have a square pyramidal shape. And when we have 2 lone pairs, we have square planar. So here it's easier to have the lone pairs of electrons in the axial position as opposed to up here where we see our lone pairs of electrons in that equatorial position. So these are what we're concerned with. Remember, we want to know the geometry of the molecule. We're not concerning ourselves simply with the arrangement of the electron pairs because we notice they'd be the same, tetrahedral, tetrahedral. So what's the actual shape? So that's why we're going with shapes or geometries, not the electron pair arrangement. So that's valence shell electron pair repulsion, and it's really good for once you have your Lewis structure, we can predict the shape because we know that the shapes exist. We can do X-ray crystallography and say, yes, this is what methane looks like, and these are the bond angles. This is measurable stuff. So another theory that we have is called valence bond theory. So we look at things are bonding because their valence electrons are participating. Here, this term bond enthalpy just means the energy that's held within the bond. So we notice there's a lot of energy between the hydrogen atoms, not as much energy between the fluorine atoms. We notice that the length here between these two things, more energy gives us a smaller distance between the 2 atoms. Smaller energy gives us a larger distance between the 2 atoms. But if we think about it, hydrogen is smaller than fluorine. So the proton in each of the hydrogen nuclei can be closer together than fluorine. Fluorine has more electrons, which are going to shield it. So we can see or propose that this bond with hydrogen is formed because the 2 1s orbitals overlap. We can assume then in fluorine that instead of the s orbital, we have 2 of the 2p orbitals overlapping. So valence bond theory comes from the idea that bonds are formed from sharing electrons from overlapping atomic orbitals. So we talked about s, p, d orbitals. So if we imagine those orbitals just overlapping, they're sharing some space, which then means if they're sharing the same space, then the electrons can also share the same space, therefore forming a bond. So how can valence bond theory be used to predict the bonding between nitrogen and hydrogen in ammonia? So here we have a nitrogen electron configuration, 1s2, 2s2, 2p3. We have 3 hydrogen atoms, each with an electron and a 1s1. So we can imagine that hydrogen is going to place its electron, or its electrons, in the 2p orbital. So we would see, or we would expect, that we should see an overlap between each of the p orbitals and each of hydrogen's s orbital. Now, what's the problem with this? We have to think about those p orbitals. They are only aligned along the axes px, py, and pz. So if this were true, then we would see that the hydrogens would be coming off, for example, at the top, over here, and over here. They'd all be 90 degrees from each other. But that's not the case. The actual bond angle between the H and H is 107.3 degrees. So how can this be? If valence bond theory says orbitals have to overlap in order to have a bond, but yet these directions of these orbitals are not allowing us to do that, how do we make up the discrepancy? So we talk about the hybridization of orbitals. So when we do this, you're looking at mixing 2 atomic orbitals on, say, the central atom. So take an s orbital and a p orbital, mix it together, what do you get? Take an s and a couple p's, what do you get? Take an s and p's and a d, what do you get? So the hybrid orbitals have different shapes from their originating orbitals. Now, the number of hybrid orbitals that you get is equal to the number of the atomic orbitals you used. So when you take an s and a p, that's 2 orbitals, so we get 2 sp orbitals. If we take s, p, p, that's 3 orbitals, so we would get 3 sp squared orbitals. Now, when we are forming covalent bonds, they either are formed because we're overlapping atomic orbitals, or overlapping an atomic orbital with a hybrid orbital, or overlapping 2 hybrid orbitals. So, formation of the sp3 hybrid orbitals. I take 1 s orbital and 3 p orbitals. So I count them, 1, 2, 3, 4, which is the same as 1, 2, 3, 4. I get 4 sp3 orbitals. So I notice now that I don't have this figure 8 shape that's as distinct. I've taken this and mixed it, and now I've got these 4 different hybrid orbitals that come off along the edges of a tetrahedron, or the corners of a tetrahedron. So with this idea, then, we can see why is it that when I have a central atom surrounded by 4 atoms, I have a tetrahedral shape. Well, that is because the carbon atom has hybridized its s and its 3p orbitals to form sp3 hybridization. Also, in the ammonia, which we just started discussing, we see the trigonal pyramidal shape, but it's based on the tetrahedral electron pair geometry. So we have this space for the electron pair to be up here, and then this allows us to actually see, yes, we do have the 107.3 degree bond angle, which is predicted. So that was sp3 hybridization. Anytime you have 4 things, whether it's lone pairs or bonded pairs, lone pairs are atoms, 4 things around a central atom, it has to be sp3 hybridization. So what happens if we don't take all the p orbitals? Let's just take 2. So I'm going to do sp2 hybrid. And once again, I'm mixing 3 orbitals. So I'm going to get 3 new orbitals coming out on the other side. So with hybridization now, I see that my orbitals are actually bigger. They extend further than what they do normally. And now we're at the corners of a triangle. So sp2 hybridization allows us to see things that have a shape that is trigonal planar. And we see the correct bond angles, which would be predicted, which would be 120 degrees. So this is sp2 hybridization. Anytime you have three things around a central atom, atoms or lone pairs, it is sp2 hybridization. Okay, so let's just take one s orbital and one p orbital and mix them together, which then leaves us two what we call unhybridized p orbitals, and this will play an important role later. So I'm mixing two orbitals, so I get two new orbitals out of it. Notice I have this nice extension along these axes now. So I get a linear shape. Central atom, two things. We see that it's linear, 180 degrees. So hybridization allows us to say, hey, this matches the idea of the shapes that we see for these molecules. The shapes exist. How do we explain why we see the shapes that we do? Well, we explain it by saying that orbitals can hybridize. Atomic orbitals can combine in a special way to give a better orbital for overlapping, for sharing those electrons. So once again, we draw the Lewis structure. We count the pairs of electrons, and we've already done this because we did this to predict the shape. So lone pairs and bonded atoms. 2 electron domains gives us sp. 3 gives us sp2. Right, we're just counting, and s plus 2 p's gives us 3. 4 things, we end up with sp3. We need 4 orbitals if we're going to have 4 things around it. So we always start with our lower energy orbitals first. 5 things, well, we've used the s, we've used all 3 p's, so now we add a d in the mix, sp3d. I have 1, 2, 3, 4, 5 orbitals coming together to form 5 new hybrid orbitals. This allows us to have 5 things around a central atom. And lastly, we have 6 total electron domains, right? This is just lone pairs plus bonding pairs. So now we see an sp3d squared. 1, 2, 3, 4, 5, 6. 6 atomic orbitals came together to form 6 new hybrid orbitals that we call sp3d squared. And this allows us for any of our octahedral arrangements. So with Lewis structures, we've counted the bonding pairs, the lone pairs to give us our shape. We also can look then just at the total pairs of electrons that we've counted up, and that allows us to predict our hybridization. So here I'm showing, once again, 2 things around it, sp. 3 things around it, sp squared. 4 things around it, spp, which is just sp3. 5 things around it. We have 1, 2, 3, 4, 5, right? sp3d. 6 things, an s, 3 p's, 2 d's gives us sp3d squared. And now we're allowed to have 6 things around this central atom, whether they be electron pairs or other atoms. So hybridization allows us to also predict, or it helps us to explain how we can have double bonds and triple bonds in a particular molecule. So let's start with carbon. And we see the ground state electron configuration. We've ignored the 1s2 electrons, but we have a 2s2, 2p2. Well, we can go to an excited state, which simply means we're going to take one of these s electrons and put it in an empty p orbital. This is allowed. We're not breaking any rules. It's just where the electron is located. So now we can take one of the s, or this 2s orbital, and mix it with 2 of the 2p orbitals to form 3 sp2 orbitals, leaving one of the orbitals unhybridized. So this p orbital is staying the same as it was. By doing this, we see here's my sp2 orbitals that are hybridized, and then I have my unhybridized orbital here. So when we look at ethylene, and this was a structure that you had to draw in the lab, we notice that we're going to form a single bond here, overlapping sp2 orbitals. We're going to form single bonds between the hydrogens by overlapping the sp2 orbital and the 1s orbital on hydrogen. Hydrogen's never going to have a hybrid orbital because it only has one orbital. So we see this overlap of atomic orbitals and hybrid orbitals. Now, if we just see single bonds here, we will notice that carbon would not have enough. 2, 4, 6, we know carbon needs 8. So what happens is these unhybridized p orbitals, if we take this image and lay it flat where we see these bonds coming out, we have these unhybridized orbitals above and below that plane, because this is a trigonal planar shape, above and below the plane. So now these unhybridized orbitals can overlap as well, sharing electrons, which allows us to have that double bond. So anytime we have a single bond, we call it sigma. Sigma for single. S is for single, S is for sigma. When we are overlapping unhybridized p orbitals, the p is for pi. So we have a double bond here, which is 1 pi bond, and then we see that we have 1, 2, 3, 4, 5 sigma bonds. So once again, sigma bonds are single, pi bonds are multiple bonding, and the pi bonds are coming from our unhybridized orbitals. So once again, we can look at some electron density maps for ethylene. We have the trigonal planar aspect of how carbon is bonding to its hydrogens and the other carbon, right? This is flat, it's like a piece of paper. And then above and below the plane, we have these unhybridized orbitals that are able to overlap and share an electron above and electron below. We can imagine it like that. Our electrostatic potential map here shows that we see more electron density above and below the plane than where these hydrogens are coming out. So double bond here, we see more electrons, right? Red means electron rich, blue means electron poor. So sp2 hybridization can allow us to form one extra bond, so a double bond. What happens if we want to form more than a double bond? Well, we go into sp hybridization. So we're going to once again start with our ground state electrons, promote the electron up to an empty p orbital, and just take one of the 2s, or well, there's only one 2s, a 2s orbital, and one of the 2 p's, and hybridize them. So now we have 2 sp orbitals, but we also have 2 unhybridized p orbitals. So what does this look like? Well, once again, we have our linear shape, which comes from our sp orbitals. So hydrogen is overlapping the 1s orbital with carbon's sp. These 2 carbons are overlapping their sp orbitals. And this carbon is overlapping its sp orbital with hydrogen's 1s orbital. So we have a sigma bond, a sigma bond, a sigma bond. We also have our unhybridized p orbitals here that are able to go above and below this imaginary line. And then if we can picture the y orbitals going around the outside. So we have above and below, and then it's almost like hugging. Like these py's are reaching around the sides there. So one's reaching above and below, the others are reaching around to the side. Let's hug it out. Let's hug out our unhybridized p orbitals. And to me, this is a funny picture because it looks like a hot dog. So I have my sigma bonds and I have my pi bonds, which are occurring above and below the plane and then around to the side. So this allows me then to see that I have that triple bond action happening for acetylene. And this was also a structure you drew on your lab. So sigma bond, sigma bond. One of these is always a sigma bond. And now we have 2 pi bonds. So when you're counting out sigma bonds and pi bonds, we don't count 3 pi bonds because you cannot have a pi bond without having a sigma bond first. Think about it. You can't have a double bond without having a single bond present. So counting this out, I have 1, 2, 3 sigma and 2 pi bonds. Remember, those pi bonds come from unhybridized p orbitals. We have to keep in mind that electrons repel each other. So if we try and shove a bunch of electrons into one space, it's not going to work out. But we know that this bonding occurs. We know that things can triple bond because we can look at bond energies and bond lengths. So this theory helps us to prove why we see what we see. So the bonding in CH2O, which is formaldehyde, if I count this out, Sigma bonds, pi bonds. I have 1, 2, 3 sigma bonds and 1 pi bond. So carbon here has to be sp2 hybridized, and the oxygen also has to be sp2 hybridized. So carbon has its sp2, has its 3 sp2 orbitals. Hydrogen has its 1s, so we have atomic overlap here. Oxygen has its sp2 orbitals, right, 3 of them. We see it overlapping with carbon's sp2 orbital. And then oxygen has a lonely p orbital. Carbon has a lonely p orbital. So once again, we see that stretching then of those p orbitals above and below that central plane in order to form multiple bonding. So if you're going to have a double bond, that means that both atoms participating in the double bond have to have the same hybridization. They both have to be sp2. If you have a triple bond, both of those atoms have to be sp hybridization. Single bonds, it's tricky because it doesn't necessarily matter. Some of the orbitals aren't even hybridized. So just for double and triple bond, we know that double bonds have to be sp2, triple bonds have to be sp. Now, the only exception to this would be if you have a central atom that has 2 double bonds coming off of it, then it would have to be sp hybridized because it's really looking at it has 2 sigma bonds and 2 pi bonds. So if an atom has 2 pi bonds, regardless of whether it's a triple bond or 2 double bonds, it has to be sp hybridization. So a single bond, just for review, is 1 sigma. A double bond is a sigma and a pi. And a triple bond is a sigma and 2 pi bonds. So we always have to start off with a sigma bond. So acetic acid, which is vinegar, how many sigma bonds and how many pi bonds do we have? 1, 2, 3, 4, 5, 6, 7 sigma and 1 pi. So hopefully we were able to count that out. All right, so valence bond theory is really great for helping us to understand why we see the geometries that we do. Now, each of these theories has its strengths and its weaknesses. So there's experiments that can be done that show that oxygen is actually paramagnetic, which means that it has parallel spins happening. So this is liquid nitrogen being poured in between a magnet and it sticks. If it didn't stick, it would be because it wasn't able to be magnetic. Now we look at the Lewis structure and we see pair of electrons, pair. Everything is paired up. So we would expect it to be diamagnetic, but it's not. The physical property exists. How do we explain it, right? This is part of the scientific method, trying to explain why we see what we see. So now we have molecular orbital theory, which is different. Here we say that bonds are formed from the interaction of atomic orbitals, which form molecular orbitals. So valence bond theory said, I'm going to hybridize my own orbitals. I'm going to rearrange my shapes so that I can be better at bonding. Here in molecular orbital theory, now we have 2 atoms coming together saying, hey, let's mix up our atomic orbitals together to form a new molecular orbital so that we can be better at bonding. So here we have a molecular orbital diagram. And what we're looking at is taking, this is a hydrogen, diatomic hydrogen. And we have 1 electron in the 1s orbital. We have 1 electron in the other hydrogen's 1s orbital. And we come together and form 2 new orbitals. So this rule is the same. However many orbitals you're mixing together, you get that many orbitals out of it. We have a bonding molecular orbital, which is lower in energy, and it is more stable. Notice we have a sigma here. That's showing that we have a single bond. Our anti-bonding molecular orbital is higher in energy, and it's denoted with a star, okay? Now, why would we have bonding versus non-bonding or anti-bonding? We have to think back and remember that The atomic orbitals are really a representation of a wave function. So we can have constructive interference and destructive interference. When we constructively interfere, our waves are going to overlap and intensify, and we see bonding. If we have destructive interference, excuse me, we see that the wave functions are going to cancel each other out, and we have antibonding, or we see this node here. So the orbitals cannot come together. So a better picture here to show constructive and destructive interference. I have two waves. Notice they are in sync. If I add them together, I see that they have increased in their amplitude. Sum of these two waves is a bigger wave. So this would be bonding. When I have waves that are out of sync, if I add these two waves together, they cancel each other out. There is no wave, and we see antibonding. Now, we can do the same thing with our p orbitals. We can have constructive interference or destructive interference. So constructive, once again, our p orbitals are going to overlap those wave functions, and we see that we can bond then. These two p orbitals have come together to form a new molecular orbital. Or we can have destructive interference, where once again we have this node going down, and we have antibonding. They're basically facing away from each other. They cannot come together to form a new molecular orbital. So sigma, right? We have sigma. We have an antibonding sigma. And notice we're always going to label. Our p orbitals come together to form sigma p orbitals. Once we form that and we have other p electrons, then they can come together to form pi molecular orbitals. So with our sigma, sigma bonds are always going along the axes. Your pi bonds or your pi orbitals are always going above or below the axes or around to the sides. So destructive and constructive interference with our pi orbitals show that we have that overlap, which we saw when we did our hybridization, that we could come together. So we have a bonding molecular orbital versus our anti-bonding molecular orbital. We have that line down the middle that is a node. Nothing exists there. They're facing away from each other. They did not combine constructively. Excuse me, my throat's getting sore. So what are our rules for molecular orbital configurations? Very similar to electron configurations. So the number of molecular orbitals formed is always equal to the number of atomic orbitals combined. So you take a 1s orbital, combine it with another 1s orbital, we end up with two orbitals. One will always be bonding and one will always be anti-bonding. So the more stable the bonding MO, the less stable the corresponding anti-bonding MO. When we fill our electrons, we always fill from low to high, right? That's the Aufbau principle. We're building up. Each molecular orbital can accommodate up to 2 electrons. So very similar to looking at our atomic orbitals, right? An s orbital holds 2 electrons. A p orbital holds 2 electrons. A d orbital holds 2 electrons. We're always going to use Hund's rule when we add electrons. So that's we maximize our parallel spins when we have degenerate orbital levels. And the number of electrons that you start with have to be the number of electrons that you end with. So however many electrons each atom is giving to form these molecular orbitals have to show up in the molecular orbital diagram. So predicting stability through bond order. And bond order is really just looking at what is the bond that is happening there. Do I have a single bond? Well, then it's 1. If I have a double bond, the bond order is 2. If I have a triple bond, the bond order is 3. We can also see that we have halves. So I'm looking at the number of bonding electrons minus the number of anti-bonding electrons, and then I divide by 2. So 1 minus 0 is 1, divide by 2, 1/2. 2 minus 0 is 2, divided by 2 is 1. Did I say divide by 1/2? I meant multiply by 1/2 or divide by 2, whatever. Here I have 2 minus 1 is 1, divided by 2 gives me 1/2. Here I have 2 minus 2, which is 0, divided by 2 gives me 0. So what is this looking at here? Diatomic hydrogen. with a positive charge means I've taken away one of the electrons. So I've taken an electron out of a bonding orbital, so I've decreased the stability of this molecule. Here I have regular hydrogen. Each hydrogen brings one s electron, so it has its 1s orbitals combining. I've got my bonding orbitals down here and my anti-bonding orbitals up here. So my bond order is 1, stable. And it's true in our prediction because there is a single bond between the hydrogen atoms. Helium, diatomic helium with a plus charge. So each helium atom brings 2 electrons in its 1s orbital. Take one away because it's a positive charge. So I have my 2 here, I have 1 up here, which gives me my bond order of 1/2. Diatomic helium, 4 electrons, 2 bonding, 2 anti-bonding, which means they cancel each other out. And this also makes sense because we know that helium doesn't bond with anything. We don't see diatomic helium. So using molecular diagrams, we can predict bond orders and also predict stability of what's going to happen if we add or remove electrons. Notice when we went from this situation to this situation, we removed an electron from a bonding orbital and we went down in our bond order. We decreased the amount of electrons that could be shared in this bonding orbital. When we increased the number of electrons in an anti-bonding orbital, so here we started with 1, we ended with 2, we noticed that our bond order went down. So putting electrons in anti-bonding orbitals decreases our bond order. Putting electrons in bonding orbitals increases our bond order. So looking at some pi molecular orbitals, we just had a simple, when we were combining our atomic 1s orbitals. So what happens when we combine all of our 2 orbitals? So this order applies for boron and nitrogen going across there. Oh, sorry, boron, carbon, and nitrogen. We don't mix up our s and p orbitals. So this is the energy that we see. Sigma 2s, anti-bonding sigma 2s. We have our sigma 2p. We have our anti-bonding sigma 2p. And then we have our 2 pi orbitals and our 2 pi anti-bonding orbitals. So we see that only s orbitals interact with s, only p orbitals interact with p. Oh, I misspoke. This is not boron, carbon, and nitrogen. This is oxychlorine and neon. So there's no mixing, there's no interacting of our s and p orbitals. We notice a different arrangement when we have carbon, boron, carbon, and nitrogen. So we see a difference in the placement of where our sigma orbitals are in comparison to where our pi orbitals are. So we actually fill our pi orbitals before we fill our sigma orbitals. They're actually lower in energy. And this is because we see some mixing of the s and p orbitals. So this arrangement is for our diatomics and lithium, which is a metal, but really this helps to explain more molecular covalently bonded molecules. So boron, carbon, and nitrogen. And when we use these molecular orbital diagrams, once again, we're looking at how many electrons does carbon start with and its orbitals. How many electrons does the other carbon start with and its orbitals? How do they come together, and then where do we fill our electrons? So, delocalized molecular orbitals. Here's the benzene ring. And what we see here is each of these carbons is sp2 hybridized, right? Because we are allowed to have 3 things around it. That tells me sp2. I have single bonds going to each of these hydrogens, and right now I have single bonds in between each of these carbons. But that only allows for 6 total electrons in each carbon. So what we see is there's actually alternating single double bonds, or in this hexagon, we have our unhybridized p orbitals, which can all form basically like a donut on top, a donut on bottom. And so all those electrons can be shared above and below. And this is what we see. So we say they're delocalized because they're not truly existing just between these 2 carbon atoms. and these two carbon atoms and these two carbon atoms. No, what we see is that the electrons are shared over the entire structure, which actually gives it a high amount of stability. And let me just take it back a couple slides. And I just want to say that in class, we're going to practice filling these orbitals. I'm going to draw molecular orbital diagrams on the board and see how these electrons fill and what it means when we can take out electrons or add electrons, and how does that affect bond orders. And because they're different, when we look at boron and nitrogen versus oxygen and fluorine, we see differences in whether they're paramagnetic or diamagnetic. Sorry about that. Just had a thought there on wanting to share something with you. All right, so these last couple slides are really just looking at comparing different ideas of bonding and the different theories. So Lewis theory, right? We're taking our electrons and we're able to draw a structure on a piece of paper. So we can have a qualitative prediction of bond length, because with that we can say whether something is a single bond or a double bond, and double bonds are stronger and shorter than single bonds. Weakness is that it's just two-dimensional. So I draw it on a piece of paper. I could draw something to be linear, but it doesn't necessarily mean that it is. So real models are three-dimensional, and it fails to explain why bonds are formed. So VSEPR, its strength, we know, is we can predict the shape of May molecules. What about June? No, sorry, that should be many. Predict the shape of many molecules and polyatomic ions. Woo, that sentence needs work. So we predict shapes, right? We count our total number of electrons and decide or see which ones are bonding and which ones are lone pairs. Weakness, it has nothing to do, it tells us no reason why the bonds are actually formed, because VSEPR is just based off of Lewis. So we draw a structure, we count our total number of electrons so we can predict the shape. Valence bond theory. So now we actually have a way to say this is why these bonds are forming. Why? Because atomic orbitals are overlapping. The weakness here, it fails to explain the bonding in many molecules. So if we're just overlapping atomic orbitals, we had that example of ammonia where it said, hey, wait, this can't be. So we expanded and said, okay, hybridization of our atomic orbitals. Now we've extended our VB theory using hybrid orbitals, so we can explain then the geometry and the bond angles in a much better fashion. Now, the weakness is it fails to predict some important properties such as magnetism, which then we got into molecular orbital theory. So the strength is accurately predicts the magnetic and other properties of molecules. So bond order, bond length, bond strength, things like that, molecular orbital theory does a really good job of. But the weakness of this is it is very complex. It's confusing. It's somewhat difficult to use those diagrams. But if we take all of these theories and put them together, we get a nice understanding of how is it that atoms can come together and share electrons. How do we see the shapes that we see, the bond angles, the lengths, the strengths, and other properties like magnetism. So within this chapter, we learned how to predict the shapes, we learned how to predict the hybridization, and we learned how to use molecular orbital diagrams. And like I say, we will be practicing all of these things in class. So make sure you get those Lewis structures down, because without being able to draw a correct Lewis structure, you can't get the right shape and you're not going to get the right hybridization. So make sure you're practicing drawing those structures, and go into the chapter and read about these different theories. See and let it help you to understand them better, because this is part of the conceptual side of chemistry, and this is just as important as just being able to draw structures. All right, y'all, good luck studying.